Okay, and all right, so happy Monday, you guys. And it is week 9. It's kind of crazy, but and it's already March. It's March 1. So now we're in the month of March. It's week 9. Next week's our last week. And anyway, today we're talking randomization tests. On Friday, we did hypothesis testing. We were looking at t-tests, comparing the means of two samples. Here we'll do some more review of hypothesis testing, this time comparing proportions, and then we'll introduce randomization tests. Okay, so this is a completely made up scenario and made up data and made up numbers, so I have no idea. Okay, don't I just made up the numbers so that they work out nicely in the problem, not as if they're like based in reality here. Okay, so the question is the proportion of international students different for stats majors and applied math majors, right? So you can major in stats or you can major in applied math, and I think we have a pretty good mix of students, some minoring in stats, some minoring in applied math, some majoring in one or the other or something else. Anyway, so let's say I got a random sample of 150 students majoring in stats, and we survey them, and we find that 75 of them are international students. And then we get a random sample of 160 students majoring in applied math, and 64 of them are international students, okay? And the question is, does this provide evidence that the proportion of international students is different for students majoring in statistics and for students majoring in applied math? Okay, now this is kind of a silly setup because, you know, at our school, you could technically go to the registrar's office and they would have a list of everybody who's majoring in math and majoring in statistics, and they could tell you the international status of these students and things like that. So we could get the answer from the population directly. But here we're going to pretend that we can't and that we got these random samples. And so somehow we got these random samples, and we're going to go off of this. And so what we're doing is we are comparing the proportions of two samples. And this is what our data that we observed says, right? And for the statistics major, 75 out of 150 students are international. And so our observed proportion, our p hat stats is going to be 0.5. Okay, 75 out of 150 is 0.5. Okay, for applied math, 64 out of 160. So if you do 64 divided by 160, your observed proportion there, your p hat math, is going to be 0.4. Okay, and so the difference between proportions that we observed is going to be p hat stats minus p hat math, or 0.5 minus 0.4. We get a difference of 0.1. Okay, and again, this is just made up data. I purposely picked these numbers just so that they're easy to work with. Okay, so we observe a 10 percentage point difference between the proportion of stats students, 0.5, and the proportion of math students, 0.4. And so what we're going to do is we're going to do a two proportion z-test. All right, and so I believe this is a test that should have been covered in your stats 10 class or your AP stats course. With a categorical variable like this, you could also conduct a chi-squared test, and you would do something similar but different. But here we're going to take a look at the two proportion z-test. And so we're going to say, for the null hypothesis, we would say that the proportion of international students is going to be the same for both majors, right? Or another way of stating that is that the difference between the proportion of international students for the two majors is 0, that there's no difference, that there's 0 difference. And so symbolically, we would write the null hypothesis is that p stats minus p math is equal to 0, okay? P being the proportion in the population, versus over here we have p hat stats minus p hat math. These are the sample proportions that we observed. That difference is 0.1. But what we're saying in the population is that p stats and p math, where p is the proportion of international students, that difference is 0. The alternative hypothesis is that the difference between proportions is not 0. P stats minus p math is not equal to 0. Is that what we're going to say here? All right. And so if the null hypothesis were true, whenever you take random samples, if this were true, we would expect our p hat stats and our p hat math, we would expect those proportions to be the same, okay? But we got a difference of 0.1, right? And so the question is, could we get a difference of 0.1 just from randomness, or is that difference of 0.1 statistically significant? Is there something actually, does that actually provide reason to believe that the proportions, that p stats minus p math is something other than 0? That's what we want to know. Okay, and so we can use the central limit theorem in this case. Technically, this is, it's a categorical variable, and you're looking at some kind of proportion. But what I think you've learned, at least in 100B, is that even with proportions, proportions can be approximated with the normal distribution, as long as your sample size is large. Okay, and so we can also, when you combine two normal distributions, you also get a normal distribution. And so here we're going to say the difference between proportions. Okay, when you take a random sample, two random samples, and you calculate the difference between sample proportions, that difference can be modeled with a normal distribution. It's going to be centered at 0, because we would expect, if the null hypothesis were true, we expect our sample proportions to be equal. But again, it's random, so sometimes you get too many international students in one sample and too few in another, and sometimes the opposite, you get too few in one sample and too many in another. And so because it's random, sometimes you get proportions that are not, that the difference is not 0. Okay, and so the standard error for this, or standard deviation for the sampling distribution, is given by this formula over here. And this is just a formula from, again, from Stats 10, your intro stats class, or your AP stats class. And I'm not going to bother kind of reviewing or deriving this, but I'm just going to say this is what it is. Okay, and I hope you guys believe me here. And this quantity p hat is the overall proportion of, I guess, international students. So it'd be kind of the total number of yes in the numerator and the total number of observations in the denominator. Okay, so I've got y1 plus y2 in the numerator, divided by n1 plus n2 in the denominator. This is kind of like pooling our data together, which is what we do when we're dealing with proportions and categorical variables, right? For the t-test, you actually have two separate types of tests. You have the Welch test and whatnot, whether you decide to pool your standard deviations or not. But here with the z proportion test, the null hypothesis is assuming that the two proportions are equal. And so to kind of estimate the overall proportion, we kind of combine all of our data together. If we were making a confidence interval, we're not making that assumption explicit. And so you'd actually treat p hat 1 and p hat 2 separate in a confidence interval, but we don't have to get into that. So here we're going to have to calculate a p-value for the proportions, the difference in proportions that we observed. Okay, and so we want to know, what is the probability that if the null hypothesis were true, okay, that that we would produce kind of two random samples where the difference between them is 0.1 or something more extreme, because that's what we observed, right? We got a random sample of stats students and a random sample of math students. The proportion of international stats students was 0.5. The proportion of international math students was 0.4. So that difference was 0.1. That's what we observed. And we want to know what is the probability of getting a difference of 0.1 just from randomness, if the populations actually do have the same proportion. Okay. And here, because we're interested in either a positive or a negative difference, we're going to use the absolute value here. Okay, we're going to take the absolute value of the difference. We're interested if there were more international students majoring in stats than math, and it would also be interesting to us if there were more international students majoring in math than statistics for this example. All right, and so here is the kind of the computational steps for getting our p-value. So the overall p hat, there's around a 45%, 0.448 proportion of international students out of the kind of the three, we surveyed a total of 310 students, and there's a total of what, 139 out of 310 or something is around 0.448. Okay, and then we calculate our test statistic Z, which is going to be the difference between the proportions we observed. We observed a difference of 0.1, and then the standard error is given by this formula. And so we get a Z-score of 1.77, pretty much 1.769. And so this difference of being greater than 0.1 can be reduced to, what's the probability that Z is greater than positive 1.769, or plus the probability that Z is less than negative 1.769. Okay, so here I go to the Z table, the normal table, or I use P norm on the computer to get kind of the area to the left and the right of these values. So the area to the right of 1.769 is 0.0384. The area to the left of negative 1.769 is 0.0384, or I can just multiply the tail area by 2, and this is going to be my p-value. My p-value is around 0.0768. Okay, around 7.7 percentage points would be my p-value. So my p-value is 0.0768. That's my p-value. So if the alpha, our significance level, is 5%, our p-value of 0.0768 is greater than alpha, all right? And that means we're not going to reject the null hypothesis. And we would say that the data we have does not provide evidence that the proportion of international students is different for statistics majors and applied math majors. So we're just saying we don't have evidence that there's a difference. You got 50% in this sample and 40% in this sample. So, you feel like you've got a 10 percentage point difference, which you do, but it turns out that you can get a 10 percentage point difference from just random sampling. So we're saying that, if the proportion is the same in the populations, okay, when you take random samples, you'd expect them to get the same, and we got something different, okay? But we're saying that it turns out the math shows us that the random sampling process can still produce 2 random samples where the difference is 0.1, okay? And this is going to happen just from random chance with a probability of around 0.0768, around 0.07, around 7 to 8% of the time. This is not a huge probability, but it's not small enough for us to just dismiss it, right? And kind of our arbitrary threshold is that if it's less than 5%, if it's going to happen less than 5% of the time, I'm going to just dismiss it and say, it's not going to really happen. But here it's going to happen, a little bit more than that, around between 7 to 8% of the time. And so I can't just completely dismiss it. And I can't just say, well, you know what? I got a difference of 10 percentage points. It doesn't happen all that often by random chance. So what I have to say is that, but it still could happen by randomness. And so I'm not ready to just dismiss it. And so therefore, I'm not ready to reject the null hypothesis. I have to say we're not going to reject the null hypothesis. Okay, we can't say that it was caused by something other than random chance. Is that okay for the conclusion here? All right, and I know I've gone through this a little bit quickly. Normally when I'm teaching intro stats 10 or something, we would probably spend like an entire week covering hypothesis tests and comparing proportions and things like that. And here I just did it in 15 minutes, but I'm assuming this is a review and that you're comfortable with these ideas. So let me go ahead and give you your first quiz answer for today. It is 9th week Monday, and our first quiz answer is D. D as in dog. D as in dog is our first quiz answer. Okay, the Z proportion test that we've just done is a parametric test. It relies on the central limit theorem. We're assuming the sampling distribution follows a normal distribution, okay? And I don't know if you guys remember, but in order to apply the central limit theorem, you often have to check if certain conditions and assumptions have been met to use the central limit theorem. And in the case of using the central limit theorem for categorical variables, like where you're using proportions, your samples have to be large enough, okay? And the consensus is kind of that if you need to have at least 10 yes and 10 no's for your sample to be large enough. You need to have at least 10 yes and at least 10 no's in both samples. And that criteria is met, okay? We had 150 people in our stat sample, 75 were international, so that's 75 yes, and 75 were domestic, so 75 no's. Both of those numbers are bigger than 10. And then the other group, we had 160 students, 64 of them said yes, I'm international, 96 would have said no, I'm not. So both of those numbers are bigger than 10. So we have no problem using the Z proportion test here. But on the other hand, if the sample size condition is not met, then using the Z proportion test could give us the wrong p-value and could lead us to making the wrong conclusion, okay? Especially if you're kind of on the edge of whether to accept or reject, reject or fail to reject the null hypothesis. And in that case, we might have to use a randomization test or some other kind of test. And so today we're going to take a look at the randomization test. And then later on this week, on Wednesday, we'll take a look at the bootstrap test, which is very similar, but slightly different from the randomization test. And we'll talk about those differences, as we cover those topics. Okay, so for the randomization test, I wanted to introduce this video from Mythbusters, okay? But in the last class, it didn't work. So the link worked, but I was not I'm not able to kind of stream the video over. To start this over, we put way too. People said that they just see a black screen. Is that what you guys are saying? Yeah. Okay. So it's too bad. And I tried. I spent a few minutes last lecture trying to figure it out, and we couldn't figure it. I couldn't figure it out. So unfortunately, I can't show you the video. All right, and I'm sorry about that. So I'm going to have to just describe what happened in the video, okay? So basically, the premise was on Mythbusters, which is this, show where, they have these people testing out, these urban legends and these myths and things like that. And the one that they wanted to test in this video was, is yawning contagious? And they tried to do some kind of scientific study to decide if yawning is contagious, that if you see somebody yawning, it prompts you to want to yawn yourself, okay? And that there's this idea that yawning is contagious. And so they decided to set up an experiment. And what they did for setting up the experiment was they kind of got this trailer where there was like a few different rooms, and they got volunteers, and they had 50 volunteers, and they lined up the volunteers to go kind of sit inside the trailer. And basically all they would do is right before the person sat inside the trailer, and the trailers are just basically, you sat inside this little closet, and there's video cameras watching you, and there's nothing else going on. There's nothing happening inside this thing. You just sit there for a few minutes, maybe 5 to 10 minutes, 15 minutes. I don't know how long they had to sit there. And they just video you to see if you yawn or not, okay? But the catch is, for some of the people, the host, Carrie, she would yawn right before they went to sit down inside the room, okay? And then other people, she would not yawn, okay? And so I think they said every third person, she would not yawn. So basically, she would, yawn for 2 people, and then every third person, she would not yawn, and they would just go sit, and then they would just watch them. And they wanted to know if the people who saw her yawn right before sitting down, were they more likely to yawn or not, versus the people where she just said, sit here, and that was it, okay? And so, at the end of the study, they had 50 people participate, and they said, this was our biggest study yet. This is our biggest sample yet, where they got 50 people. And okay, so this is what happened. Some people see a person yawn, that's the seed yawn, and other people did not. That was the control group. And then the team watching on video cameras record who yawns and who didn't, okay? And so they said, we had a sample of 50, and the difference was basically in the group where they saw the seed yawn, 29% ended up yawning, okay? And in the control group where they didn't see anybody yawn, only 25% of those people ended up yawning, okay? And at the end, the narrator, well, they say, you know what, this was our biggest sample. They said, the difference isn't dramatic, but this is our biggest sample yet. And it does seem to influence, and that they're saying that, this number 29.4%, 0.294 is greater than 0.25. And therefore that indicates that yawning is contagious. And they say, the narrator says, there's little doubt it does seem to be contagious, talking about yawning and how that seeing somebody yawn is the reason why these people were more likely to yawn than these people, okay? And that's pretty much the premise of the video. It's more fun than my description here, but that's what happened, okay? And so, I don't think you can, so I had to actually pay for this video, but it's not really worth, well, I shouldn't. It's up to you, but but you don't have to watch it, okay? And so technically they said every third person was selected to be in the control group, okay? But the order of people who lined up, they had 50 people line up, and that we could treat the ordering, the order of the people who lined up as a kind of a random thing. So we basically treat who got assigned into the control and who got assigned into the treatment group to be a random process, okay? Because depending on, how they lined up in a row, that lining up is kind of random. And so who ended up, being every third person in the control group, we can treat that as a random thing. So what do you guys think? 29% versus 25%, or 0.294 versus 0.25. Do you think that difference is significant or not?
Probably not, but maybe. I don't know.
Yeah. All right. Well, we can do a test, right? We'll do a randomization test. Okay. So we would set up our hypotheses like this. So we're going to call P seed. Okay. This is the probability of yawning if you're in the seed group. Okay. This is probability of yawning given that someone's in the seed group. And we've got P control. This is the probability of someone yawning if they're in the control group. And our null hypothesis is that yawning is not contagious, or that P seed minus P control, that the difference between them is 0. Okay, that there's no difference. The probability of yawning, whether you're in the seed group, or the probability of yawning, whether in the control group, has no impact on it, that the difference between these probabilities is 0. Okay, and then the alternative is that yawning is contagious, meaning that if you're in the seed group, you are more likely to yawn. Okay, if you see somebody yawn, you're going to be more likely to yawn while you're waiting inside the trailer than if you didn't see someone yawn. Okay, that would be the yawning is contagious, and that would be P seed minus P control is greater than 0. Okay, and so when we observed our data, we got 10/34 for the seed group. Okay, that's the 29.294 proportion. And then we had 4 out of the 16, or 25%. And so, 0.294 minus 0.25, we get a difference of 0.044. And if the null hypothesis were true, we would expect, our sample proportions to be equal. We would expect a difference of 0. We got a difference of around 4 percentage points, 0.044. And we want to know if that was statistically significant or not. Okay. So what we have to do is we're going to kind of establish what would happen if the null hypothesis were true, right? So if the null hypothesis were true, then whether a person yawns or doesn't yawn is not related to whether somebody got a seed yawn or not, okay? And so if the null hypothesis were true, then the difference that we've observed in our results, the fact that this was 0.294 and this was 0.25, that difference is just a result of the random assignment of treatments, okay? that some people were going to yawn anyway. And so this is a little bit of a strange idea, but another way we could think of it is just that, we had a total sample of 50 people, and 14 of those people were just destined to yawn. These people were going to yawn. It was their destiny to yawn during the experiment. And whether they were in the control group or whether they saw somebody yawn and they were in the treatment group where they got a seated yawn, that they were going to yawn anyway. That whether they yawned or didn't yawn had nothing to do with the treatment that they received. Okay. And so the fact that we observed 29% yawn in one group and 25% yawn in the other group is merely a result of the random assignment. Or another way to say it is that randomness alone could produce the difference between proportions of 0.044. And what we want to do is we want to calculate a p-value. The p-value is the probability of getting the difference that we've observed, 0.044 or something more unusual, if the null hypothesis were true. Okay. And so if we assume that the two populations have the same proportion of yawners, what's the probability that just random assignment could produce samples where one is 0.294 and the other is 0.025, okay, or where we get this difference of 0.044 or something more unusual? That's what we want to do. We want to figure out what's the probability that we're going to get 0.044 or something more unusual. And so what we're going to do is we're going to do a randomization test, okay? Now, basically all of these tests, we have to make some kind of assumption to fill in our gaps of knowledge, right? So when you do kind of a Z proportion test, you're assuming the central limit theorem holds, you're assuming that your sample is representative of the population, all of stuff like that, okay? In our case, when we're doing a randomization test, we're making some assumptions, and one assumption here is the exchangeability of outcomes. And the idea in exchangeability of outcomes is that under the null hypothesis, all kind of permutations of the data are equally likely. And that any permutation of the data is exchangeable with any other permutation of the data, right? And then that's like a weird mouthful to say, but at a practical level, this just means that exchangeability only applies where your data was obtained via an experiment where random assignment was used, okay? If random assignment was not used in the gathering of the data, don't use a randomization test. So in our case, we can kind of, although the assignment itself wasn't random, we can treat how the 50 people lined up as a random thing, right? And so if the experiment was held on another day or something like that, even with the same 50 people, they might have gotten into a slightly different order. And then, and in that case, we would have had different assignments, right? Every third person could have been a different person, and we would have gotten a different arrangement of assignments of who got treatment and who got the control, okay? And that would be the case where, and basically, that's what we've got here, okay? We can treat how the arrangement, every permutation of the 50 people that participated in the experiment to be exchangeable with any other kind of ordering of people. And so, and we're gonna just treat this as like 14 out of the 50 people were just gonna yawn anyway. It didn't matter that they were in the control group or the treatment group. They were just gonna yawn anyway. And so that's what we wanna do, right? So we're going to say if the patients or the participants, get treatments assigned randomly, then any arrangement of patients or participants is equally likely. But in other cases where if you did like some kind of observational study, okay, and so the treatments, in our case, the treatments might be some kind of condition, like this person chooses to smoke, and we want to know if there's, some kind of relationship between smoking and some other kind of disease or something like that. That's not a random thing, okay? It's like who chooses to smoke is not random, okay? Or whatnot. And so so we can't treat every single permutation as equally likely. We can't just say, oh, On another day, it's just as equally likely that these people were going to smoke and these people were not. Okay, so in those cases, there's you can't do you can't use a randomization test for data coming from an observational study. Okay, so anyway, going back, this is kind of just some preliminary stuff for doing the randomization test. Okay, here, before I get into that, let me give you your second quiz answer for today. Second quiz answer for today is E. E as an elephant. E as an elephant is your second quiz answer. E. Okay. All right, so what we're going to do is we're going to get our data into the computer. So remember, we had 10 out of 34 people, 10 out of 34 people in the seed yawn group who yawned, 34 participants, 10 yawned, and in the control group, 16 participants and 4 yawned. Okay, and so here I'm going to just create a vector of length 50, and I'm going to say, all right, we have 10 people who yawned. We're going to have true 10 times. So true represents that they yawned. False represents that they didn't yawn. And so we're going to say 10 true and 24 false. And this is going to represent kind of the first 34 people will be, you know, the 10 people who yawned and 24 people who didn't yawn in the treatment group. And then in the control group, we had 16 people, 4 of them yawned and 12 did not. Okay, and so I have this vector of true and false values here. All right, so I've got a logical vector of length 50 here. And we're going to just say, okay, the first 34 yawning from 1 through 34, that will be the treatment group. And then the remaining 16 I'll put in the control group. Right, so basically treatment is a vector of length 34, where 10 are 10 trues and 24 falses. And control is a vector of length 16, where 4 are true and 12 are false. And then I can say, well, what is the mean of treatment? Okay, so even though this is a logical vector, R is going to coerce the trues to 1s and the falses to 0. And so a mean of a logical vector is basically the proportion true. And so the mean of treatment is going to be 10 out of 34. I get a proportion of 0.294. The mean of the control group is going to be 4 trues and 12 falses. That's going to be 4 out of 16. And so the mean of the control group is going to be 0.25. Right? And the observed difference I have between proportions, that observed difference is going to be the mean of the treatment, 0.294, minus the mean of the control, 0.25. 0.294 minus 0.25 will give me an observed difference of 0.044. Okay, so we have a difference of around 4.4 percentage points for the difference between proportions in the treatment group versus the control group. All right, is that okay? Just getting the data into R by using kind of these logical vectors here. Okay, so to do the randomization test, I'm going to use the sample function. Okay, what sample does is if you give a sample of vector, it will just shuffle the vector. It will maintain all of the elements in the vector. It will just change the order. Okay, there's different options you can use with sample. You can do like replace equals true. You can say sample size equals 3, and you can specify how many values you want and stuff like that. But if you just use sample with a vector and no other options, what it's going to do is it's going to take the vector and it's just going to shuffle them. It's going to return all of the elements of the vector, but just in a new shuffled order. Okay. And because I've been talking about shuffling, I accidentally typed in shuffle rather than sample, but this should say sample yawning. And the output is going to still be a vector of length 50. And there's still going to be 14 values that are true and 36 values that are false. It's just that the order is going to be randomized. Okay, it's just that the order will change. And so here is one possible outcome is that here I do set seed 1, and I'm going to take that vector of 50 values, okay, and I'm going to do sample, and this is going to be just randomized, all shuffled up, okay, and now I'm going to say, after shuffling it, we're going to put 34 into one pile, and then we're going to call that group A, and we're going to put 16 into group B. All right, So here, basically, I had 50 people. We're going to say 14 of these people are destined to yawn. And we're going to just mix them up and put some into group A and some into group B. Okay. And so here I did the randomizing myself. We know that there's no rhyme or reason why group A should have more or fewer people yawning than group B, right? This is just random. Sometimes you're going to get, so some of the 14 people who yawn will end up in group A. Some of the 14 people who yawn will end up in group B, and we're going to calculate these proportions. There's no real reason why group A or group B would have more or fewer yawners than the other. It's just, this is just the result of the random process. So here we're going to say, well, what proportion in group A ended up yawning from the random process? And we get 0.294. What proportion in group B ended up yawning from the randomization process? And we get 0.25. Okay, these happen to be the same results that we got from Mythbusters, from their real experiment where they did like an actual seated yawn versus a control and things like that. Here, I just shuffled people up and I'm getting a difference of 0.294 versus 0.25. I'm getting a random difference of 0.044. Okay. And so our random process produced this difference of 0.044 just from the random process alone. Okay. And, maybe this was a coincidence. Maybe it's not. Let's do this a few more times. Okay. But right now, it seems like just from randomization, we could get a difference of 0.044, right? So, Mythbusters, they were like, oh, the difference of 4%, not dramatic, but seems like to be a significant difference. Maybe it is significant, or maybe it's something like this happens quite a bit, okay? Here I do another trial, okay? I just shuffle up the 50 people, okay? Again, 14 of them are destined to yawn. We have 14 yawners in the group of 50. And we're going to put 34 into group A after mixing them up, 16 into group B. In group A this time, 0.235, 23.235 ended up yawning in group A, and in group B 0.375, okay? And so, we want to know, are there more or fewer people in group A? So in this case, the difference between group A versus group B, the proportions, is negative 0.1397, around negative 0.14, okay? And so, so this difference of around 14, we get a difference of around 14 percentage points, but, in the opposite direction, just from randomness here. Is that okay? What's happening here? So here here we know that the only reason why there's a difference between group A and group B in proportions is just this randomizing process. I did sample of yawning. That's the only reason. It's not, the data in here is not the result of me recording data or doing some kind of yawning or anything like that. The only reason why I've got some values in group A and group B is because I shuffled up the values. So this difference of 14 percentage points is just a result of shuffling up, okay? And so let's just see what happens if I do this like 10,000 times. We're going to do this a whole bunch of times. We're going to do this 10,000 times. Okay, and so I say we're going to record all of the differences. I'm going to just create an empty vector of 10,000 values. And then every single time for each iteration, I'm going to take that vector yawning as a vector of length 50, and I'm going to just shuffle those 50 values. Okay, we're going to take the first 34 values and put them into group A. We're going to put the last 16 values and put them into group B. Any difference between group A and group B is because I did sample here. There's no other reason why there's a difference. Okay, the only reason why there's a difference between group A and group B is that I did sample and that shuffled up the differences. Okay, and so we say, well, what is the difference between the mean of group A and the mean of group B? Okay, and then we're going to keep track of all of those differences. Okay, and so we take a look at the result, and it turns out that the median difference that we get between group A and group B is 0.044. Okay, sometimes, okay, about 25% of the time we get a difference of negative 0.0477, or something more negative. About 25% of the time we get a difference of 0.136 or something more positive. Okay, And one time, just from randomizing alone, we got a difference of 41 percentage points. And one time by randomizing alone, we got a difference of around 60 percentage points in the opposite direction. Okay, and so so these are just results from just randomizing alone. There's no other reason why we're getting any of these differences. This is just the differences that we observe here is just a result of just doing the sample here. All right, and so we want to know, well, what is our p-value? Our p-value, what's the probability of observing the difference that we got in our data's observed difference, right? So when we looked at the data, our observed difference between group A and group between the treatment group and the control group, right? When we actually like yawned in front of people and gave them a CDON, and when we actually like just put them in the trailer and had them recorded their video, we got a difference of 0.044. Okay, we got a difference of 0.044. And we want to know how often do we get that kind of difference or something more unusual from just randomizing, right? So we have all of these differences that we randomize, and we want to say, okay, well, what proportion of those are 0.044 or something more? Okay. So our alternative hypothesis is that PC minus P control is greater than 0. So we're only interested in differences of 0.044 or something more positive. So I'm going to say, take the mean of differences greater than or equal to my observed difference of 0.044. Okay. And we get a value of 0.507. 0.507. So my p-value is around 51%. Okay. Because I did this 10,000 times. What this is basically saying is that, so this differences is a vector of 10,000, length 10,000, going anywhere from negative 0.59 to positive 0.41. So I have 10,000 numeric values here for different differences that we got. And we wanted to know, well, how many of those differences are greater than or equal to 0.044, right? And it turns out that what, around 5,070 out of 10,000, around 5,000 of them have a difference greater than 0.044. So the proportion or the probability of getting a difference of 0.044 or something more is over 50%. So let me just pause there, and I just want to make sure this makes sense. How I'm getting this empirical p-value of 0.507. Does that kind of make sense? The calculation why I'm comparing the differences to the observed value to get my empirical p-value. It's okay? All right. Well, great. And so my empirical p-value is 0.507. And what this means is that the randomization process has a high probability of producing this difference of 0.044. Okay. So if we had watched the video, the narrator concludes, you know, we have, I don't know what they say, but it's like, it seems pretty clear that that yawning is contagious because, you know, we got a difference of, you know, 29% versus 25%. Okay. And they're basically saying that 4 percentage point difference is an indication that seeing somebody yawn makes the person more likely to yawn. Okay. But it turns out that a 4 percentage point difference could just happen quite easily just from randomization alone. Okay. And so really our data doesn't provide any reason to believe that that difference of 4 percentage points was caused by something other than randomness. Okay. Because when we did it by randomness, it happens quite a bit. Okay. So we would not reject the null hypothesis, and we would say that the data does not provide reason to believe that getting a seed yawn makes a person more likely to yawn. Okay. On the other hand, I cannot say that yawning is not contagious. All we're saying is that our data does not provide evidence that it is contagious. Okay. You know, maybe it's possible that seeing somebody yawn makes the probability that they're going to yawn higher, and maybe we just didn't collect enough data. Okay. Or maybe we got some weird results. All right. Who knows? Maybe we got a bunch of yawn resistant people. Who knows? I don't know. Okay. Interestingly enough, if you had an alternative hypothesis, right? Does seeing someone yawn have any effect, a positive or negative effect on someone else yawning? Okay. Then we would use a two-sided alternative. We would be interested if seeing somebody yawn makes you more likely to yawn. We would also be interested if seeing somebody yawn makes you less likely to yawn. Okay, we'd be interested in any kind of difference. Okay, and in that case, we would use the absolute value. We would use kind of both sides. We would want to see a difference of 0.044 and something more positive versus 0.044 and negative 0.044 and something more negative. Okay, and so if we did this, what's the absolute value of the differences being greater than or equal to our observed difference? What's the mean there? The p-value turns out to be 1. You get a p-value of basically 100% probability. Okay, and that might be surprising. Like, how do you get a p-value of 1? Well, it turns out because we have, a fairly small data set. This is these are the results here. Okay, in our data set we have 10 out of 34 versus 4 out of 16. 0.294 minus 0.25, we get a difference of 0.044. And here I just showed like some of the different results that you could get. If instead of 10 versus 4, 10 in group A, 10 yawners in group A, and 4 yawners in group B, we're assuming we're going to have 14 people who yawn total. If I had 9 in group A and 5 in group B, I would get a difference of negative 0.047, okay, which is greater than 0.044. If I had 8 in group A and 6 in group B, that would result in a difference of negative 0.139, okay? The difference of 10 in group A versus 4 in group B gives me a difference of 0.044. And then if I had 11 in group A versus 3 in group B, then I would get a difference of 0.136, okay? And it's hard to get, more extreme, I mean, we get more extreme, but the numbers just keep getting bigger. And so it's actually impossible to have a difference of proportions that's any smaller than 0.044. It's not possible to get a difference smaller than 0.044 because any other arrangement of the people is going to give you either a difference of negative 0.047 or negative 0.139 or 0.136. You can't have a difference smaller than 0.044, okay? So Mythbusters was kind of celebrating, we got a difference of 4 percentage points, maybe it's not a dramatic difference, but that definitely shows that yawning is contagious. It's actually impossible to get a difference smaller than 4 percentage points between the two groups. So, so I would say, our data does not provide any evidence that it's contagious or it increases the probability of yawning. Okay, so so that's what we get. All right. Do we have any questions there? No. Okay, so that's it for randomization tests. Let me give you your last view quiz answer for today. Last view quiz answer is C. C as in cat. C as in cat is the solution there. Okay, we'll end here for today, and we'll see you guys on Wednesday. So have a good evening.
Professor, quickly,